So one of the things we need to talk about very, very briefly is efficiency. And let me tell you where efficiency comes in. No motor in the world is perfectly efficient. And what that means is, I've told you before that what comes into a motor or any circuit in the world is called apparent power, right? That's what you're sucking up. You're taking in VAs, volt amps. And you calculate that by just multiplying the number of amps times the voltage, volt amps. Nice simple calculation, right? So, but what is the motor actually doing with that power? Is it turning it into, for every 746 VAs, is it turning into 746 watts of cranking force? Absolutely not. Nothing does that. Nothing is perfectly efficient. Now, what you need to know about efficiency is that what you take in is your bottom number of a fraction. That's your input, right? So your VAs are what you put in, and your watts is the cranking force. It's the real work that's getting done, and that's measured in watts. So let's say, let me go to the bottom of this. This is going to be odd, but let me go to the very bottom of this slideshow and add a slide. I think I have one spare slide down here that, or two, and it's not going to go. I love that. Damn it. Got to be quick. Okay. So let's say that we have a single phase 120 volt motor, and just, okay, so let's pull up an example of a real motor, and we're going to find out what its efficiency is, because we can see what it pulls in for power, right? We're looking at a 1 horsepower motor. How much work does a 1 horsepower motor do at the very maximum? 746 watts of cranking force, right? And that's a certain number of foot-pounds of torque in a certain amount of time, which is what James Watt really talked about. But let's look at this motor. Our apparent power is what comes in. You can actually measure it with an ammeter and a voltmeter, right? And it's taking in 230 volts. We're going to say that it's going to get a full 230 volts, and it draws 8 amps at the maximum. Now, if we just multiply 230 times 8, we get okay, so we're going to look at this 1 horsepower motor, and we're going to say we can see that it's going to produce 1 horsepower of cranking force. It draws 230 volts at 8 amps, and that is 1840 volt amps. That's its power coming in. Okay, and it's going to crank out 746 watts of power. So we can see that its efficiency is 746 over 1840. That's a fraction, isn't it? Now, if we divide 746 by 1840, we can see that we get a decimal efficiency of 0.405. Decimal 4.405, if we turn that into percentage, we all know that we multiply that times 100, and we get 40.5, 40.5% efficiency. So you don't mind paying for work being done at 40%, do you? Yeah, you do. You don't want anything being done at 40% efficiency, do you? Okay, I mean, think about this. Somebody's cleaning your car, and they're going to charge you 60% more than it took them to do it. I mean, that's not a good deal, 40% efficiency. And a lot of motors. Now, where does the code book get these crazy numbers of this ampacity? They test a lot of motors, and which ones do you think they said is the code book ampacity? The least efficient that draw the most current to do the same work. Is there a motor that only draws 5 or 6 amps? Yes, there is. What is 90% of, let's say 100, let's divide 746 by 0.9. Divide by 0.9, not multiply. 828 VAs. There are motors that only take in 828. Now let's write that down. How many is it? 0.8. Thank you. Okay, now let's divide that by 230 volts and see what current it would be drawing. How many? 3.6 amps. The code book says this motor draws 8 amps because it has to look at the cheapest. I usually mention a certain country, but I won't do that because we're being recorded. The cheapest possible motor in the whole world that runs the most inefficiently of any motor in the whole world. It's going to draw 8 amps. And in the worst case scenario, a 1 horsepower at 230 volts will draw 8 amps. But a very, very efficient one, which will cost 2 or 3 times what that piece of crap motor will cost, will only draw 3.6 amps. It's 90% efficient. Are there motors like that? But they cost a lot of money. Now, why would anybody spend 2 or 3 times as much money on a motor just because it draws less current? Because you pay for the current, and you always pay for the current. If you're running a motor, let's talk about this real quickly, because this is kind of a point that's going to come up as a big deal in the second semester. Not this one, but next semester. We're going to talk about this efficiency stuff a lot. Because if you're selling an installation, and you let everybody give them a price on the absolute cheapest crap they can put in, is that the kind of work you want to do? Okay, I made a living never ever doing that, or very seldom doing that. I would always wait until everybody had talked to the owner about their bid, and I'd go say, are you done getting all these cheap shit bids? And he says, what do you mean? And I said, well, they're not spending your money the way I would spend my money. Do you go buy the least efficient car you can buy that costs the least amount of money? Or do you go buy a more efficient vehicle that costs you more money? And a Prius is a great example. A Prius costs, 30 or 40% more than a regular car, right? A Prius is $40,000 for those who don't know. That's a lot of money. When there are cars that you can buy for $12,000, $13,000, $14,000, at $15,000, cars are fairly common. You've got a choice of 40 or 50 cars at that, right? And you get up to $20,000 and you have hundreds of choices, right? So I'm just saying that for the amount of money, you have choices at every point, right? So the point is that if I were spending my money, would I go buy a big turd of a vehicle that gets 12 miles the gallon just because it's cheap to buy it right now this second? I wouldn't spend my money that way because I want to have a lower cost in the long run. And you really have to look at the long run. So if you're going to talk to somebody about doing this, you've got to know how long is it going to take before the expensive cost of this motor is going to catch up with the high cost of the cheap one running more efficiently. Now, 230 volts, what is 8 minus 3.6? Okay, 4.4 amps at 230 volts. Multiply that together. It's going to be about the operational cost of the cheaper motor, right? It's almost half. It's less than half. So what we're going to do is we're going to take the 4.4 amps times 230 volts, which is 1,1200 volt amps per hour. Volt amp hours. Watt hours, Edison would call it, but it's not really watt hours, is it? Watts is real work getting done. This is wasted energy. Okay, and 2,000 hours is the normal 40-hour work week, and taking a couple weeks off at Christmas and taking off some other holidays, you'll work about 2,000 hours a year. Now, really and truly, most factories run more like 2,500 or 3,000, but you can't depend on that, so we're going to figure 2,000. And about a nickel an kilowatt hour, and I forgot we have to divide by 1,000, so 1,1200 times 2,000 times 0.05 divided by 1,000 is what? No, it's $101. It's $101 every year that you're going to save because you bought the more efficient motor. Now, that doesn't sound like a lot of money, but the motor, the cheap shit one, was probably $200. And the really good one was probably $500. What's the difference? $300. What's the return on investment? 3 years. Now, those are wild ballpark numbers because electricity costs more than that, and I've rounded a lot down so that really and truly, probably this thing will pay for itself in about 2 years, which is a good thing. That means that 2 years from now, he's going to have another $100 a year spare that goes in his pocket because he didn't pay Edison that. And the year after that, and the year after that, and the year after that, and the year after that. So that motor is going to pay him for at least 8 years. Not at least, but most likely more than 8 years, $100. He's going to make an extra $800 over the next 10 years compared to buying the cheap motor that he could have done. Okay, so that's why efficiency is important. But efficiency is a very simple idea. It's what is being taken in, 1,840 VAs. What work is being done, 746. What efficiency is that? 40.5%. And that's all you really need to know about efficiency. Now let's go back to the top of the slideshow and start over. Okay. Now it does want to go to the top. Okay. This is a slide presentation built by me, for you, and no one else. My students. The American wire gauge is an offshoot of what was an original tool manufacturer called the Brown and Sharp Company. They created a wire gauge, and everybody just kind of caught on. You need to have a wire. You need to be able to size wires if you're building machines, right? Okay, so that's what they did. It's mostly used here, and it has to do with cross-sectional area of the wire. And it's measured in circular mills, and in the 116 class, you should learn what a circular mill really is. We're not going to discuss that much, except that it's the diameter in mils. So 0.163 becomes 163 mils, right? 0.163 inches is 163 mils. Okay, and that squared is circular mils, which is kind of a crazy way to do it, but that's the way we've been doing it for like 100 years, so what are we going to do now? Okay, wire size are inversely proportional to the number that represents them, meaning that when you see a number like 30, that is a tiny little wire the size of a hair. Okay, when you see size 0, that's a big wire. Now, back in the Brown and Sharp time, it only was as big as 0 at first, and then they started needing bigger and bigger wires, and they went all the way up to 4/0. They don't say 40, they say 4/0. 4/0. If you say 40 wire size in a wholesale house, people are going to kind of look at you funny. So if it's 4/0, not 40, even though you write 4/0 or 0000, that's 4/0. 3/0 is smaller than that. 2/0 is smaller than that. 1/0 is smallest of those. And when you see circular mill area, that's the newer standard for bigger wires because the American wire gauge or the old Brown and Sharp system stopped at 4/0. That was as big as wire got back then. So now anytime you see a number of, say, 250 kc mill, that's 250,000 circular mills. Nice, simple idea. I don't know why we didn't go with that, but what the heck. So we've got this crazy system, and we're kind of stuck with it. It's like, why are the roads as wide as they are? Because that's how wide the ox carts and the carts were that were pulled that got the settlers to California. Okay. Let's see. The standard is 4 solid wires. And if you see a specification where it's got 3 different numbers, it's telling you how many strands of stranded wire and how big those strands are. So there's a different system for that. This is our American wire gauge. I know this is not terribly easy to read, but that's okay. We're going to go to one that's a little easier to read. But you'll see where it goes from down here. The smallest number you're used to seeing is about 14. And you'll notice that it has a 64 mil diameter. And that means it's got 4,107. I've never seen 4,107. I've only seen 4,109 as its cross-sectional area in circular mills. I bet if we take 64.08 and square it, we'll get 4,107 or 4,109. So they laid this thing out so that if you went up 2 sizes, skip 2 sizes, go up 2. In other words, 3 sizes up, that you will have double the cross-sectional area. Now let's look at the cross-sectional area in square inches. Cross-sectional area in square inches. Now this is at 20 degrees, and we would all agree that we don't operate at 20 degrees. Our table does not begin at 20 degrees, begins at 30 degrees. Anything below 30 degrees down to 20 degrees gets a positive deration factor, correction factor. Anything above 30 degrees, as we well know, gets a negative deration factor. In other words, we're going to derate the ampacity of the wires worth above 30 degrees. So anyway, the square inches area, let's look at a number 14, has 0.003225 square inches. So we go up 2 sizes. We skip 2, 13 and 12, go up to size 11. And we see that we have 0.006 square inches. That's twice as many square inches of cross-sectional area, right? Okay, and it works that way all the way up the table. Okay, and that's something we need to be aware of. So if you're trying to go, you know one wire and you need to go have twice that ampacity, you can just go up, skip 2, that third one above it is going to have double the cross-sectional area. And they laid it out that way intentionally so that it was easy to find a larger wire with more ampacity. As I said, stranded wire gauges they take up a little more cross-sectional area because the individual strands have air in between them. Shocking, I tell you. And because of that, even though once they've got a jacket on them, they're very often a little bit bigger. What is the advantage to stranded wire? There's a whole lot of them. Skin effect, corrosion resistance. There's a lot of advantages to stranded wire. It's easier to pull. One that's most important to me. It's easier to pull. Now, we need to talk about voltage drop. We're going to talk about getting 230 volts to where we want to go. So we've said before a couple of times that 2 kilo circular mill gives you VD. That's the one you're going to remember because it's kind of got a tricky thing in it that makes your mind see somebody chasing you down with a spear possibly or something like that. But 2 kilo circular mill gives you VD. And this is for single phase circuits only. Okay, for 3-phase circuits, we use square root of 3 times kil over circular mil gives you VD. Now, both of those formulas are not particularly useful. The one that is more useful is we're trying to find the size of the wire that we actually need. We have to find the voltage drop that we will allow and plug that in where VD is. I don't know how I wound up getting this CVD in there, but I apparently didn't erase enough of that thing before I dragged it in there. And so you know that should be VD. So we're going to do a couple calculations with that in a minute. And let's go down a little bit and take a look at this. You've been told to find the ampacity of a wire by multiplying the original. In the book, it says find the ampacity of a wire by multiplying the durations. Now let's say that in our book it says a certain wire is good for a certain ampacity. And let's say that 14 THHN, which is 90-degree wire, is good for let me go to 31016, which is where we find the ampacities. And let's look at a number. Let's take a bigger wire. Let's go to a number 8. And a THHN wire, if it has 90-degree terminals, then we could use it at 55 amps. 55 amps is its original ampacity. Now, if we take that through an area that has a, let's say, 70-degree centigrade area, which is pretty hot, that's 158 degrees, it's now only worth 0.58. And we also are going to run it in a conduit with 5 other current carrying conductors. So it's got 6 current carrying conductors in this conduit. So we have to take what duration for that? 80%. So now let's multiply 55 times 0.58 times 0.8, and we're going to get a lot less than 55 amps, right? What are we going to have? Say again? 25.5 means less than 25 amps. 25 or less amps. So here we have this big number 8, and we can only use it for 25 amps. Now, that doesn't tell us what we need to know, though, does it? That says, okay, this wire is no longer good for what we originally had in mind for it. But what we want to know is the other way around. We want to divide by the factors, and we want to find our actual wire ampacity that we need and then select that. So let's say we have our motor that's only 40.5% efficient. And let's say that we're going to use that same single-phase motor, our inefficient one. And it drew at 230 volts single-phase, 8 amps. Okay? Now, that is our full VA. That's going to give us our VA. But what we normally would do is we would look at, we need 746 watts of cranking force, and this particular motor is only 40.5 efficient. We're going to get rid of this point there. We're going to put it back in decimal form. And that will give us what? 746 divided by 0.405. Okay. 0.75? 975. We don't care about all that stuff. It's going to take 1841.42 watts of power that we need to put in, right? Now we're going to take that, and matter of fact, we're going to change that to 42 right now. We're going to divide that by 230 volts. And we find that it's 8 amps. Okay? Now, the problem is, can we supply a motor that has a full load ampacity of 8 amps at 8 amps? No. A motor that runs continuously will draw more as it heats up. So we need to allow more than this. So let's take all of this and get rid of it, or most of it. Let's get rid of this right here. We're going to multiply our 8 amps times 125% because the code says that we must do that. So 8 times 1.25, 10 even, 10 amps. Now, a number 14 should be more than sufficient if it were within 75 feet. But let's say that, again, before we decided that we were going to go through a very hot room that has we said we were going to go through a 70-degree centigrade room, and that's a 0.58 duration, right? We also said that it was going to be one of 6 current-carrying conductors going out to the load area, and that is a 0.8 duration factor. So this is the number of amps we really need to supply on what the wire needs to be able to supply on a continuous basis. And we're going to divide that by 0.58 times 0.8. So to do that with our calculator, we're going to hit clear a couple times. We're going to put in 10 divided by left parentheses 0.58 times 0.8, right parentheses, enter, and we get an answer. And that answer is okay, so if we find that it's 13.79 amps, our number 14 wire will still be good enough because a 14 will allow, according to our chart, okay, so that was an error. If we divide 10 by 0.58 times 0.8 has a quantity, we'll get 21.55 amps. And number 14 will no longer be big enough. It says to have 21 amps, we need to go up to number 12. I take it back, number 14 as a 90-degree wire will do 25 amps. So we could still use number 14 because a high temperature wire like a THHN or a THWN will give us that kind of ampacity. No, we were talking about using 14 because it's only drawing 10 amps. Now this is an abnormal case because the motor is so small. Normally, when you have a high temperature and several current carrying conductors in a conduit, it's going to change the wire. Now let's go to a bigger motor just so we can find a more appropriate application of this rule. Let's do one more. All right, for our second example, we want to look at a 1.5 horsepower motor. And a 1.5 horsepower motor draws 20 amps at 115 volts. And just out of curiosity, I thought we should look at the efficiency. So it's going to draw 2,300 VAs. That's what you're paying for. And the power it's going to put out is a 1.5 horse, which is 1,119 watts of power. So that means that that motor, this cheaper motor, is only 48% efficient. That's not very good. Okay, so now let's look at, once again, we're going to take the ampacity, we're going to multiply 20 times 1.25, and that's what, 25? So we need wire that will supply 25 amps, right? Now, if we're really close, number 14 will work, right? Because if we have high temperature connections, our number 14 is good for 25 amps on the nose. So it's fine. We don't have to have more amps than we need. We just have to have enough. So 25, we would use a number 14 wire. But now let's say that we're going out through our high temperature area. Let's pick a different one. Let's get a more reasonable. We're going on the roof of a building in Antelope Valley. And on the roof, 4 inches above the roof, it's 140 degrees Fahrenheit. That's 60 degrees centigrade, 71% deration factor. So we're going to take our 25 amps and we're going to divide by, what was it, 71? Was that right? 71%. And again, it's in one of 6 current carrying conductors in a conduit. And so we're going to have to take an 80% deration also. So now we're going to take 25 and divide by, left parentheses, 0.71 times 0.8, right parentheses, enter, and what do we get? So what we're finding out here is we need a wire that actually will carry 44 amps. Now, assuming that we have the high degree temperature terminals, we can go over here and we can find a wire. Now, number 10 won't do it because it'll only carry 40, and that's not enough. So we've got to go up to a number 8, which will carry 55 amps. Okay? Everybody understand that idea? So this is how we would select the wire. Now, our book more specifically guides us on how to find the derated ampacity of a wire, but that's not what we really want to know as electricians, right? We want to know what wire should we use, right? Now, what's our other deration factor? Distance. And if we have excessive distance, we need to use the 2 kill formula. Anything over 75 feet. Anything over 75 feet, if you're doing a house, as an example, anything that's more than 75 feet from the sub panel, you better go to a bigger size wire because you're going to have excessive voltage drop. Now, the voltage drop formula is not part of the regular code, but it is part of the fine print notes. And City of County of Los Angeles, from what I understand, they included the fine print notes as part of the code, meaning that that is part of code. You must not have too much voltage drop. So let's say that we have our motor that requires 25 amps again. And we know that we had a 20 amp FLA. But after a long period of time, it's going to be creating the same heat as a 25 amp motor because over a long period of time, everything gets hotter and hotter as we go along. So let's say that we're going to consider 25 amps as our full load ampacity, or what we want to be able to supply to the motor. And we're going to have 2 times 10.8, which is our K. Our current is our I, 25 amps. And then our L is our distance. And let's say we're going out 150 feet. That's actually not that far, right? 150 feet is a fairly reasonable amount of distance. Now, are we going to divide by the circular mill and find the voltage drop? We could do that, but we don't want to do that because if we plug in the normal size wire of 14, which we would use nice and close, we don't want to do that. We want to find out what wire we really need to use, right? So let's plug in. We don't want to allow, and it's coming from a sub panel, so we don't want to allow any more than 3% of our supplied voltage, which is 120 volts. 3% of 120 volts is what? 3.6 volts. So we have 2 times 10.8 times 25 times 150. Hit enter after that, and then divide by 3.6. And it'll give you the cross-sectional area of the wire that you need to use. So what number do we get? And that's circular mil. Remember, 2 kilo over circular mil, or 2 kilo over the voltage drop gives you the circular mil. Now let's go to our charts. That's not the one. Is it? Conductors for, no, that's not the one we want. We want none of those. Where did I put it? I know I put it in here, and now I don't see it. Is that it? Nope. That is a really blurred slide. And I think that's the one that we need. No, it's not. It's not even in here. All right, so what we need to do is, lost all our drawings, but we know that we need 22,500 circular mil area. And so we would go to Table 8, Chapter 9 in our code book, or we would pull it up on the right slide if it had made it onto the slide somehow. And I believe it's number 6. How many circular mils does number 6 have? 26,000 is more than 22,500 by a considerable amount. Now when, okay, we're going to use 26,000, what was it, 26 even? 250, thank you. So that means we could now take the wire that we're actually going to use and find our actual voltage drop, right? So let's go back to our formula. 2 times 10.8 times, what was it? 25 amps times 150 feet. Is that right? And then we're going to plug in 26,250. And that'll give us our voltage drop, because that's 2 kilo over circular mil, right? Oh, everything I just wrote is gone. Gotta love that. Okay. Times 10.8 times 25 times 2 KIL 150 feet, all over 22,500. And that's equal to what? How many? No, it's less than 3.6. Okay, so we wind up with 3.6 anyway. We're still losing 3.6 volts. And having gone to a slightly larger wire, I would have thought we would have a little less than that. But that's okay. We still have an appropriate amount of voltage getting to the motor. It's going to be 120 minus 3.6 is our actual voltage at the motor, which changes our current, by the way. That's why you're always interested in what current is flowing. If you have a lower voltage, the current's going to go up for the same amount of power, right? Because motors are perfect servants. They try and do the work no matter what voltage they're getting. Do what? Oh, that's the circular mil area of the wire we started out with. Okay. Good. And we're plugging in 26,000 what? 250. Now let's get our actual voltage drop of the new circuit, and it's going to be a little less than 3.6 volts. Now put in 2 times 10.8 times 25 times 150, divide that by 26,250. What do we get now? Pulled it out completely. I wonder how long that's been now. Good. How much is it? Okay. Okay, so we find, oh shoot, it just dropped everything out. We find that if we do the math, we find out that we actually only drop 3.0 something volts, which is an improvement over 3.6. And it doesn't sound like a lot, but remember, over 2,000 hours a year, it's going to make a lot of difference. Okay, I think that's enough on this subject.